Precise taping corrections. The topics in this video include systematic errors in precise taping, equations for the correction of those systematic errors in precise taping, and an example problem removing systematic errors from a measurement using a 100-foot steel tape. Tape calibration is necessary before we do any precise taping. What that is the actual tape length is usually different than the nominal length, and so we must find out how long is the tape really compared to a standard of 100.0000 feet. And so we'll take that tape and compare it against the standard calibration length at preset conditions. Example calibration conditions include temperature of the tape at 68 degrees Fahrenheit, pull on the tape, commonly 12 pounds pull, and the tape support commonly is fully horizontal support throughout. There are 5 systematic errors that we'll cover in this video. First is standard length, the actual tape length. It's different than the nominal, and that's what we discover in the calibration process. Temperature, expansion and contraction of steel. We know that steel expands and contracts with temperature. Pull, we know that steel stretches when you apply load to it. So when we apply tension to the tape, we actually stretch that tape just a little bit, and then when we release the pull, it goes back to its original length. Sag, when a tape is used unsupported in the field, the weight of the tape will draw the ends in, and so we need to know exactly what the weight of the tape is and the unsupported conditions that it's being used. Slope, we convert a slope measurement to a horizontal value. Many times we want to measure on a slope on purpose, and then we want to convert it to a horizontal value using trigonometry. Standard length is our first correction. And we can see that standard length is a function of 3 parameters. L is the standardized or calibrated length of the tape. L prime is just the nominal tape length. And L is the recorded measurement of the line in the field. Temperature, we see the temperature has 4 parameters that we must deal with. K is the coefficient of thermal expansion of steel, which is 6.45 times 10 to the minus 6 feet per degree Fahrenheit. Some people say it's just 6.5. That's fine too, but I'm going to use 6.45. T1 is the field temperature at the time of the measurement. T is the standardization temperature at the time of calibration. And L is just the recorded measurement of the line, the observation. Pull. The pull equation has 5 parameters in it that are going to determine what the pull correction is going to be. P1 is the pull at the time of the measurement, the field pull. P is the standardization or the calibration tension or calibration pull. L is the recorded measurement of the line. A is the cross-sectional area of the tape. If we take the tape and take a pair of tin snips and cut the tape in half and then look down the end of the tape, that's a wee little cross-sectional area that we'll see. That's the area we're talking about. E is the modulus of elasticity of steel, which is 29 times 10 to the 6 psi. Sag has 3 parameters that will dictate the sag correction. Notice that sag is always negative. Sag is always negative. W in the equation is the weight of the tape per foot. L sub S is the unsupported length of the tape, and that's not the measured length. That's the unsupported length of the tape at the time of the tape being used. P1 is the pull at the time of measurement. So we have to be careful with L sub S. L sub S is the unsupported length of the tape, and we compute sag for each unsupported length of tape measured. So if we have a line of 350 feet, we would have 3 C sub S values computed based upon 100 feet of unsupported length, and 1 C sub S value based upon 50 feet of unsupported length. Slope correction, we can see from the triangle below that we're just taking the slope measurement of L and we're converting it to a horizontal. And we're going to use Pythagorean theorem to do that. We just solve Pythagorean theorem for the horizontal dimension instead of the hypotenuse side. And D is the elevation difference between the 2 endpoints. So we would need to know the elevation of the 2 endpoints in this particular situation. Now we apply the corrections using the following equation. The length corrected is equal to the field observation plus the sum of all the corrections, as you can see in this simple equation right here. So all we need to do is compute all the corrections for every one of the systematic errors present in the measurement and apply those to the observation in the field. We're going to go through an example problem now, and here's the description. We have a line measured with a 100-foot steel tape. The tape has a calibration length of 100.07 feet. It was calibrated at 68 degrees Fahrenheit, 12 pounds pull, and fully supported. The field observation was 477.25, and the field conditions were end support only, sag, pull of 20 pounds, so pull correction, temperature of 92 degrees Fahrenheit, temperature correction. The tape has a cross-sectional area of 0.0030 inches squared and a weight of 1.5 pounds. Determine the correct length of the line by removing the systematic errors due to length, temperature, pull, and sag. All right, let's do this. The first correction will be the length correction based upon the calibrated length. We'll pull up the length correction equation and just plug in the appropriate values. We can see that in this equation, L is the calibration length, and so that's going to be 100.07. L prime is the nominal, 100 divided by 100. It's really error per foot is what this is. And you multiply times the number of feet measured, which is 477.25. We can see from the equation that this is going to be a positive correction. The numerator is going to return a positive value, so the result will be a positive 0.033 feet. The next is the temperature difference. So the temperature equation, we need the coefficient of thermal expansion, K, and the difference in temperature. Again, if we look at the result here, look at the numbers, we can see that the coefficient of thermal expansion is 6.45 times 10 to the minus 6th. The field temperature is 92, and the calibration temperature was 68. And we multiply that simply by the measurement that we observed in the field. And again, it's a positive value here, and we know it's going to be positive because right here, the 92 minus the 68 returns a positive value in the parenthetical. Pull correction. The pull equation has 5 parameters, and we just need to plug the appropriate values into the equation and solve. We can see that the field pull is 20 and the calibration was 12. The parenthetical term returns a positive value. Again, this correction will be positive, just like the temperature correction and the standard length correction. We plug in the field measurement of 477.25 and then divide through by the cross-sectional area in inches squared and the modulus of elasticity in pounds per square inch. This equation is dimensionally homogeneous. We have pounds here, we have pounds right here per square inch. The pounds divide out, the square inches divide out, and all that's remaining is feet, giving us a result of positive 0.044 feet for pull correction. The last correction is sag, and the sag correction, we're going to have to do 2 computations. One for the full tape lengths, there were 4 100-foot measurements, and one for the partial of 77.25. So let's go ahead and compute the correction for each full tape length. And we pull up our equation. It's going to be a negative number always. The ends are always drawn in, so we have to subtract out that error. We see that the weight is 1.5 pounds. Divide through by 100 gives us the weight per foot of tape. We square that quantity, and then we multiply that times the 100, the unsupported length of the tape, and we cube that value. And then we divide through by 24 times the field pull squared. And the field pull is 20 in this particular situation. We can see that for every 100-foot tape length, there is 0.023 feet that must be removed from that tape, and it's always negative. For the partial length, well, it's the same exact equation, and the only thing that's going to change is L sub S is going to be 77.25. Everything else remains the same. So we can see that the result here is that for that partial measurement, we must subtract 0.011 feet to get the appropriate value. Now we're going to apply the corrections. Let's see here. The corrected length equals the field observation plus the sum of all the corrections. Well, let's look at them here. Here's the field length, the field observation, 477.25. Here is 0.033, and if you remember, that comes from length. The 0.074, that comes from temperature. The 0.044, well, that comes from pull. And then we have 4 times 0.023 negative. That's going to be sag for every 100 foot of tape length in the measurement. And then here is sag for the partial measurement. So algebraically sum these up, add them to L, and we get the corrected length. Corrected length turns out to be 477.298. We're going to round that to the nearest hundredth of a foot because the original measurement was to the nearest hundredth of a foot. These other digits through the calculation were just carried to protect rounding is the only reason we did that. So the answer will be 477.30 feet. In summary, we have covered the topics of systematic errors in precise taping, the equations for correction, an example problem using the 100-foot steel tape. So the outcomes from this video, what we hope you've learned is, we hope you've learned how to recognize systematic errors in precise taping, and then also learned how to apply systematic error corrections to a measurement. This is the end of the video lesson.